Hello and welcome to Lecture 3 for the UCSB course ECE 257A, Fault-Tolerant Computing. This lecture deals with Chapter 3 in the textbook entitled Combinational Modeling. So we will discuss a number of models that are combinational in nature to evaluate the reliability and other attributes of a dependable system. Okay, so here, this is where we are. We are in part 1 of the textbook, chapter 3, combinational modeling. The next lecture, state space modeling, introduces another category of models that we find useful in evaluating systems with regard to dependability attributes. Now, combinational models, if a system has only a few components and very simple connections between them, you can just directly write the reliability equations. So, for example, if a system consists of, let's say, 3 components, a processor, a memory, and a bus connecting them, then if you know the reliability of each of these 3 components, you can just multiply those reliabilities and find the reliability of the overall system. When systems get more complicated, we need a more systematic way of doing it. We may not be able to write the reliability equation directly, but we may need some help. So in order to demonstrate these methods, known as case analysis methods, I'll take the example we covered earlier. That was when you had 5 sites with connections between them, a user being at one of these sites and data being at a different site, or maybe 2 other sites or 3 other sites, and then in each case we wrote the availability equation, probability that data will be accessible with the simple non-redundant data one side, with 2 copies of the data, a home site and a mirror site, with 3 copies of the data, home site, mirror 1 and mirror 2, and also a data distribution scheme that we discussed. Okay, so let's take one of these, and this is when you have a home site and a mirror site, so 2 copies, duplicated data. And then the requester always first tries to go to the home site to get the data. And if data is not available on the home site, then the mirror site will be accessed. Continue with the assumptions we had last time. The assumptions being that in order to get data from a particular site, you need to access that site directly. So the requester, R in this diagram, goes to the home site to get the data. In order to be able to do that, this link to the home site and the home site itself must be available. Link reliability we wrote as L, and site reliability as S. So S times L is the probability that this unit, the requester here, can get the data from the home site. In other words, when both the link to the home site and the home site itself are available. Okay, if that's not the case, that has probability 1 minus SL. So SL means both of those are available. 1 minus SL means that the complementary event, and at least one of them is not available. In that case, you have to go to mirror side, to the mirror side, and that probability of success going there is S times L. Okay, so suppose that this is simple still, you can write the equation directly, but suppose you somehow have trouble coming up with this equation. Here is what you can do. You say, okay, here is the situation I'm facing. Dashed lines and dashed sites means that we don't know anything about their status. Solid means they're available. Okay, so the solid circle here means the requesting site is available. And a solid line, like this one, means that that particular link is available. So start here, say, okay, I consider two cases. First, when both this link to the home site and the home site are available, that has probability S times L. And so this is the situation. This link is available, this site is available, and then I'm done. Then with probability 1, I can access the data. If this link is not available, that has probability 1 minus L, so you see here that it's not available, it's missing. So this is a subcase that I need to analyze. Well, the only way I can get to the data is if I can get it through the mirror side. So that has probability S times L. And now suppose this link is available, but this site is not available. That's the situation. That link is available, this site is not available. Then again, I can't get the data from the home site. I have to get it from the mirror side, so that has probability SL. And the total availability is just the product of these. 1 times SL plus SL times 1 minus L plus SL times 1 minus L, S times L. Okay, so these are three cases. The important thing is that they must be mutually exclusive in order for me to be able to add these probabilities. In this case, there are either both of these are available, the link is not available, and it doesn't matter whether the site is available or not, and the link is not available. The link is available, but the site is not available. In fact, in this case, I could have merged these two branches because with respect to data accessibility, it doesn't matter whether the link is not available or the site is not available. So the sum of these two probabilities, 1 minus L plus L minus SL, becomes 1 minus SL. So basically, this reduces to that equation. So 1 minus SL, these two are merged, times SL plus 1 times SL, which is the same equation. So I already mentioned that this is a simple example. You probably don't use case analysis in this case, for this problem, but just gives you the basics of the idea. You divide the problem that you're trying to analyze into mutually exclusive subcases. And then in this subcase, for example, given that this link is missing, it's a smaller system. If needed, you can continue decomposing this into mutually exclusive subcases until you get to a point where the subcases are simple enough for you to write the reliability equation directly. Okay, now I can use the same method for triplication. Again, I say link to primary site and primary site are available, as shown here. The solid, remember, solid elements means they are available. Again, this link is not available, it's missing. or this link is available, but the site is not available. Link available, site. And then again, in this case, for example, I do a similar decomposition. This link and this site, backup one site are available, and so on and so forth. Again, I can merge these two subcases here and these two subcases here because they're really the same with respect to probability calculations. Now, in the case of the data dispersion scheme, where we have 5 pieces, any 3 of which are sufficient to reconstruct the data that we are interested in, this is basically a 2 out of 4 system. We don't need to do case analysis here because 2 out of 4, or more generally, k out of n systems occur frequently enough that we know how to write equations for them. So a 2 out of 4 system, at least 2 out of 4 units are available, is characterized by this equation. All 4 are available. That's one instance, in which case, obviously, we have more than the 2 that we need. 1 is unavailable, 3 are available, and that can happen in 4 different ways, depending on which site is unavailable. Notice that these are mutually exclusive. This one says all 4 are available. This one says 1 is unavailable. So it doesn't overlap with that. And then, but the 3 others are available. This one says 2 are unavailable. 2 are available. That can happen in 6 ways. Okay, so in this case, we use the k out of n formula to directly write a reliability equation, availability in this case. Okay, the next set of notions are those of series and parallel systems. These are very useful in our modeling activities. So what is a series system? A series system is composed of n units, all of which must be healthy for the system to function properly. So this is known as the reliability block diagram for such a system. There are 4 modules or units. They are connected in series, meaning that, so going from one side of this diagram to the other side through good units is known as a success path. So for us to have a success path from the left side of this diagram to the right side of the diagram, all 4 units must be working. So the reliability of a series system is simply the product of the reliabilities of its individual units. Of course, the units can be different, and therefore they can have different reliabilities. But we assume independent failures. In other words, things that cause this unit to fail do not overlap things that cause this unit to fail. In other words, they fail independently of each other. That's why we can multiply the reliabilities. So here is an example of a series system. There is a pipe. There are 4 valves. And suppose I'm interested in being able to allow liquid, let's say oil, whatever goes into this pipe, to flow from one side to the other side. In order for the liquid to flow from this side to the other side, all 4 of these must be open. So if one of the valves is stuck shut, meaning it is shut and I can't open it, then I'm in trouble. Then I can't allow liquid to flow from one side to the other. So all four of these must be non-shut, they must not have failed in the stuck shut mode for the system to be able to operate. On the other hand, if they fail to stuck on open mode, so let's say one of these is open and I can't shut it, then I can still control the flow of the liquid using the other three valves. So this is a series system with respect to stuck shut failures. This is also a series system, and this is the surprising part because this looks like a parallel system. It is a series system if I'm worried about stuck on open failures. So if one of these valves in this diagram is stuck on open, it's open and I can't shut it, then the liquid will flow to the other side and I have no control over it. So if stuck on open is the dominant failure mode, then this is a series system with respect to that particular type of failure. Okay. Now, implications of series system to design are as follows. The reliability of a series system is the product of the reliabilities of the component of the system. If the reliability equation is exponential, which we talked about earlier and justified it, then the product of reliabilities will be e to the power sum of the failure rates times t. In other words, the failure rates in a series system add up. So if this fails once every 10 to the 9 hours, this one fails twice every 10 to the 9 hours, then 1, then 2. So 1 times 10 to the minus 9, 2 times 10 to the minus 9, 1 times, and 2 times. Then I add these. 1 plus 2 plus 1 plus 2 is 6. So the overall failure rate will be 6 times 10 to the minus 9, or 6 failures per 10 to the minus. So failure rates add up if we have an exponential reliability equation. Going the other way, if we want to design the system composed of 4 components, all of which are critical to the system's functioning, in other words, all 4 must be working properly for the system to work properly. And if we have a reliability goal R, little r, for the overall system, that reliability goal R translates to some total failure rate. So from the reliability goal R, we find the total failure rate. And then we do something called failure rate budget allocation. So suppose these 4 units are being built by 4 different design teams. And suppose 6 times 10 to the minus 9 is the failure rate that I allow for the total overall system. Then the design manager can go to the teams and say, okay, your team here should aim for 1 failure every 10 to the minus 9. This unit, let's aim for 2 times 10 to the minus 9. So a bigger failure rate budget is given to this unit, and maybe because it's a more complex unit for some reason, okay? So the total failure rate is divided up between these teams designing various components, and each team basically aims to design the unit with that limit on the failure rate. Sometimes, as happens in design, designs are iterative. One of these teams may come back to the manager and say, okay, we tried, but we can't design this unit with a failure rate of 1 times 10 to the minus 9. Then perhaps the budget is reallocated and a higher failure rate budget is given to this team so that they can complete their design. Okay, so the key observation here is that failure rate add up in a series system. So parallel system is a system which is composed of n units, the health of one of which is enough for proper system operation. So here I've shown 4 units in parallel. So this is the reliability block diagrams. And a success path exists from the left side to the right side if any of these, at least one of these units is functioning. So the path can go through that. Okay, now in a parallel system, because all 4 of these units must fail for the system to fail, it's easier to write the equation for unreliability. So the unreliability of the system is the product of the unreliabilities of the components. In other words, this system fails if all 4 of these units, or n more generally, fail. Okay, so from this I derive R to be 1 minus the product of 1 minus Ri. That is, the system fails only if all units malfunction. So this is an example of a parallel system with pipes and valves. If I'm interested, if the valves can fail to stuck shut, in other words, if 3 of these valves even are stuck shut and I can't open them, I can still allow liquid to go to the other side through the fourth valve. So 3 malfunctions are tolerable here. 4 malfunctions are not. But if I'm interested in stuck and open valves can sometimes get stuck and open and I can't shut them, then this is a series system. Because in this case, if one of these is open, well, water will flow and I have no control. So not even one stuck and open is allowed. Therefore, with respect to stuck and open valves, this is a series system. So series and parallel do not imply that things are connected in series or parallel. You see that both parallel connection of valves and series connection of valves can give you a parallel system, depending on the failure mode that you're considering. Similarly, both series connection of valves and parallel connection of valves can give you a series system with respect to reliability. So this is something that you have to be careful about. Now in parallel systems, similarly, once we have set a reliability goal, R, then of course we have the unreliability goal, which should be the product of unreliabilities. And then we budget unreliabilities to the various units. If these units are identical, and the unreliability assigned to each of the identical units, basically the nth root of 1 minus R. Here's an example. Suppose I'm aiming for reliability 0.9999 or unreliability 0.0001, 10 to the minus 4, and I have 4 units, then each of them can have unreliability 10 to the minus 1, and I will still meet the overall reliability goal. Okay, so before going into more elaborate models, I have a couple of slides here that show you the perils of modeling. Modeling is a risky activity because if you're model is not accurate, is not realistic, then you can get results that basically have no counterpart in reality. You get results that are not realistic, and therefore you may think that your system is more reliable than it actually is, or less reliable than it actually is. Of course, if you think it is less reliable, that's safe. But if you think it's more reliable than it actually is, that's kind of risky, because then the failure probability will exceed what your model shows. Let me describe an example. This is a very interesting example. It comes in 2 slides. The statement of the problem is in the first slide and the solution in the second slide. If you want, you can pause the video after the first slide and then try to figure out what the answer is before continuing with my explanation. So here is a 2-way parallel system. In a passenger plane, the failure rate of the cabin pressurizing system is 10 to the minus 5 per hour. In other words, loss of cabin pressure occurs once per 10 to the 5 hours of flight. Now, when cabin pressure is lost, passenger planes have oxygen masks that are deployed from the ceiling of the plane. And the oxygen mask deployment system also has a failure rate 10 to the minus 5 per hour. And we get in trouble, there will be loss of life only if both of these systems fail. In other words, the cabin is depressurized and the oxygen masks fail to deploy, and therefore people cannot breathe and can potentially die. So this is a parallel system in that sense. So only if both of these subsystems fail, the total system, the overall system fails. Now here is a potential solution model for this. Assuming failure independence between the two systems, both systems fail at the rate of 10 to the minus 10 per hour. Basically, each one has a failure rate 10 to the minus 5 per hour. Multiply them, you get 10 to the minus 10 per hour. Suppose you're considering flights that are 10 hours in duration. Therefore, given that the failure rate per hour is 10 to the minus 10, multiplied by the number of hours in the flight, that gives you 10 to the minus 9 probability of loss of life due to both of these systems failing. Okay, it sounds reasonable, the model. Until I tell you that's alternate reasoning, then you start doubting whether that's the correct reason. Now, generally speaking, in safety critical systems, 10 to the minus 9 failure rate is considered acceptable where safety is concerned. In other words, it's small enough for us to accept that risk that the passengers will die with that probability over a 10-hour flight. Okay, so here's alternate reason. The probability of cabin pressure system failure in 10-hour flight is 10 to the minus 4. Okay, the cabin pressure system has a failure rate of 10 to the minus 5 per hour. Over 10 hours, it has a failure probability of 10 to the minus 4. Probability of the oxygen masks failing to deploy in a 10-hour flight is also 10 to the minus 4. Its failure rate of 10 to the minus 5 multiplied by the flight duration 10. Probability of both systems failing in a 10-hour flight, assume independence again, is 10 to the minus 4 times 10 to the minus 4, which is 10 to the minus 8. Now, why is the result different from our first analysis? which gives us a 10 to the minus 9. I said 10 to the minus 9 failure rate in a safety critical system is acceptable. 10 to the minus 8 is really not acceptable. It's a bit too high. So if the second model is correct, we are in trouble. If the first model is correct, we are okay. So this is where I want you to think about these two ways of modeling the overall failure probability and consider which one is the correct way of doing it. Okay, so I'm now going to proceed to the next slide. You can pause if you want to think about this and maybe do some calculations before proceeding. Okay, so here's a little bit more detail in our modeling. So the 10 hours of flight, I've drawn them individually rather than just one long 10-hour flight. Consider the flight as 10 one-hour segments. Okay, now suppose masks fail in that second segment, while pressure is lost in the seventh segment between hours 6 and 7. Does this lead to overall failure? Well, the answer is no, because when masks fail, the answer is yes. If masks fail and we don't know this, there's no indication that they have failed because they're just, in some compartment in the plane's ceiling. We don't see them, they failed, and we don't notice that they failed. When the pressure is lost a few hours later and we try to use the mask, they fail, they don't deploy, and we are in trouble. Okay? Now consider the second situation. The pressure is lost in the second hour and masks fail in the seventh hour between hours 6 and 7. This situation is probably safe. Even though both of these units fail, the system as a whole will likely not fail. The reason is that when pressure is lost and the masks are deployed, so the masks have not failed at that time, usually planes don't just go on the usual path and get to the normal destination. They try to land right away, return to the airport if they have just left, or find a nearby airport that can accommodate them and land there so that they can take care of the problem. So the masks failing a few hours later may not be relevant because the plane will not be in the air for that long. Okay, so what we can say is that the first model on the previous slide that gives us a failure rate of 10 to the minus 9 was optimistic, because it's sort of, when we say the failure rate of the two systems together is 10 to the minus 10 per hour, that sort of assumes that the two systems fail in the same hour. So it basically does not consider the situation where masks fail here and the pressure is lost here. Okay, so that's an optimistic model, which is very dangerous in reliability calculations because we definitely don't want to overestimate the reliability. The second model that gives us a failure rate 10 to the minus 8 is pessimistic. In other words, it considers this situation as a failure, even though, as I just discussed, it's not really a failure. Therefore, the reliability will be perhaps more than 1 minus 10 to the minus 8. How much more? We don't know, but definitely it's considering some cases as failures that should not be considered as failure. So this is the challenge of modeling. Your model is as good as your assumptions. If you are not careful and don't make very careful assumptions about the model and can justify those assumptions, then your model will not give you correct results, accurate results. Okay, now in a parallel system like the one we just considered, where there are 2 subsystems or 4 subsystems, any one of which is enough for the system to operate correctly, there is this challenge. So often these parallel systems are used in the following way. So this is one operating module, and these 3 are spare modules, replacement modules. So normally this one is working because only one is needed. And then if we detect a problem in the functioning of this module, we replace it with a spare. Okay, that spare subsequently fails, we replace that with a spare, and so on, until all the spares have been exhausted, and then the system fails at that point. Now, when we say that if the reliability of each of these is 0.9, the reliability of the overall system is 0.9999, we are basically assuming that failure detection and replacement are fully reliable, completely reliable. In other words, with complete confidence, we can detect that something went wrong here, because if something went wrong and we don't detect it, we continue to use this bad module and get basically garbage results out of it. So the success of such a system depends on proper detection failure and then proper replacement. So replacement is not a trivial thing, because if this unit is powered off, we have to power it on, we have to initialize it so that it can take over the function of this unit. Okay, perhaps initialize it with proper initial state, data, and so on. And that takes both effort and, more importantly, is subject to failure. We may not be successful in failure detection here. We may not be successful in switching over to another one of these modules. Okay, so this ideal parallel system has this reliability equation. If all the modules are identical, so 1 minus Rm is unreliability of one of these modules, to the power n when we have n modules, and 1 minus that will be the unreliability. Now I write this in the following form so that I can later compare it with the next equation. So what this is basically in the denominator, I have 1 minus Rm. The 1 and minus 1 cancel out, so I get Rm, and that cancels out with this Rm. So this is basically the same equation. Now let the probability, so we can model this imperfection in failure detection and switching over to an alternate module by something called the coverage factor. So this is the simplest way we can model that. And this coverage factor is basically the success probability for detecting a failure and switching over to an alternate module is less than 1. Of course, the closer to 1, the better. And then the reliability of the system with this coverage factor C is given by this equation. And I'm not going to justify it here. You can consult this reference, end of chapter reference, page 288, for the derivation of this. Okay, so notice that if the coverage factor is 1, C is equal to 1, C to the n is 1, this C is 1. So the formula is converted to that ideal case. If C is less than 1, then you get these factors that are less than 1. It reduces the reliability, compared to the reliability of a single module. Okay, so this is coverage factor. Now graphically we can depict that equation like this. This is n on the horizontal axis, n the number of parallel modules that we have in our system. On the vertical axis is r. It's a logarithmic scale. Okay, so if the coverage factor is 1, perfect coverage, then if you use, let's say, 4 module, you get a pretty high reliability. If you use 5 module, you get a reliability that consists of 6 nines. Okay, and similarly, it increases very quickly. If you have imperfect coverage, on the other hand, the reliability curve saturates after a while, and it does not increase beyond a certain point. So even if the coverage factor is 0.99949, which is still pretty good, after using, let's say, 8 parallel modules, and you go to 9, 10, 11, and so on. This is, by the way, also on log scale. Okay, you don't gain reliability by using more and more modules. That's because the system probably failed sometime earlier as a result of imperfect switching over between the early modules. In fact, considering C a constant regardless of the number of modules is a simplifying assumption. Usually C actually decreases, gets worse when you have more modules because the switching mechanism becomes more complicated with more modules. Therefore, the coverage declines with more modules. So these curves in practice not only flatten, but actually start dropping off after a while. So that if you use too many modules, that not only doesn't buy you anything in terms of reliability, but it damages reliability. Okay, now here you see that, for example, with this coverage factor, 0.49, if you have 7 modules and increase it to 8 modules, it buys you a little bit of reliability improvement. Not much. In fact, that increase may not be considered cost effective. Whereas the difference between, let's say, 3 and 4 modules is quite significant. And therefore, it is cost effective to go from 3 to 4 because it increases the reliability significantly. Once the curve starts to flatten, then perhaps, of course, when it completely flattens, there's no point in going to larger numbers of modules. But even before it flattens, it may not be cost effective to go to slightly higher reliability by using more modules. You may want to stop at this point, or maybe with 6 modules even. Okay, so it's basically cost considerations come into play as well. So reliability improvement should be at reasonable cost. Of course, if the coverage factor is low, like 0.9, then you're in trouble. Beyond even going from 2 modules to 4 modules, you don't experience much reliability gain. And definitely from 4 to 8 or 16, no gain is seen. As I mentioned, we probably lose because coverage factor increases with the larger number of decreases with the larger number of modules. Okay, so it's very important that this coverage factor be high if we want to gain significant reliability by using parallel modules. This implies that a failure detection should be as complete as possible so that we don't miss any failures. And then the switch over from one module to another one to a spare should also be a trouble-free process simple process that is highly reliable. Okay, the next notion, the next set of models are classes of K out of N systems, the simplest of which is 2 out of 3 system. In cars that we drive, most cars have 4 tires, and they have 1 spare tire in the trunk. And as long as 4 of those 5 tires are okay, properly inflated, you can drive your car. But again, you need a way to detect the failure of the main tires and be able to successfully switch over to the spare tire. Because if, for example, a tire blows out and you're driving, you may get into an accident and not be able to take advantage of the spare. So assuming the perfect detection of tire problem and perfect replacement of the deflated tire or blown tire with a spare, it's a 4 out of 5 system. As long as 4 of the tires work, you should be okay. So 2 out of 3 system means that you have 3 units doing a particular computation, let's say, and any 2 of them deriving the correct result will yield the correct result because I use a voting circuit, majority circuit, so that if these 2 agree and this one disagrees in terms of what it produced, the 2 that agree, okay, are in the majority, and therefore the output will be correct, assuming this voter is working correctly. Okay, so this is the reliability of a 2 out of 3 system. The system works if all 3 units work, or if unit 1 and 2 work and 3 doesn't work correctly, provides the wrong answer. 2 and 3 work and 1 fails, 3 and 1 work and 2 fails. Generally, when you use this, these 3 modules are identical. So let's say each has reliability Rm, and the reliability of that 2 out of 3 arrangement is given inside the parentheses here. And if the voter is imperfect, the reliability of the voter is also multiplied by this expression. More generally, in a K out of N system, you basically says, as long as at least K units work, I'm okay. So J goes from K to N, at least K units must work, up to all N units working. Rm to the J, this is the reliability, probability of J units working, reliability of 1 unit raised to the power J. This is the probability that N minus J, the remaining N minus J unit not working. And then Nj, N choose J is the number of ways that this can occur. So we have a closed form equation for reliability of a K out of N system. Okay? Of course, this is a perfect K out of N system if we have a mechanism here to sort of decide what the correct output is. The reliability of that mechanism must also be multiplied by this expression. So this is known as triple modular redundancy. Triple modular. 3 modules are used. It's a redundancy system with 3 modules and a voter. Now, if multiple computations are to be performed, this would be one possible arrangement. Triplicate this part of the computation, vote on the result. Triplicate the next part of the computation, vote, and so on. In this arrangement, the voters will be part of the system hardcore, meaning that if any of these voters fails, then you get an incorrect result at the output. You can avoid that by triplicating also the voters, except of course the last one, which needs to produce a non-redundant result. But in the intermediate stages, you have 3 voters and 3 results are produced. So if this voter fails, only this result is incorrect. And you have 2 correct results here. Okay? So the failure of this voter is indistinguishable from the failure of this module. So we can lump them together in reliability analysis and say here is an expanded module consisting of an original module plus this voter. So the failure rates add up. Whatever this failure rate this one had, plus the failure rate of this voter, which is typically much smaller than that of a module, will be the failure rate of this composite module. And then now we can model this as a 2 out of 3 system with that higher failure rate. This is a 2 out of 3 system. This is a 2 out of 3 system. And then this is just a voter at the end. But there's now only 1 voter, which is part of the critical core, not 3 voters as in the original design. Okay, a variant of these k out of n systems, actually 2 variants, are known as k out of n g. G stands for good, or k out of n f. F stands for failed system. What does this mean? This means we have a system consisting of n modules, n units, and as long as k consecutive ones of those modules are good, the system is good. And this one says we have a system of n modules. If k consecutive modules out of those n fail, then the system fails. Let me explain this one first because it's easier, more intuitive. Suppose I have a system of streetlights. So each streetlight is one of these n modules. And the objective of streetlights is to provide enough lighting on the sidewalk or street for people to be safe. Okay? Now, if one of these lights fails and it's not immediately fixed, then you will have less light in this area because light will have to come from this light and this one. Let's travel a distance to get there. Therefore, there will be less light. Maybe that's not unacceptable. You know, if one of these fails, then we still have enough light to ensure safety. But if 2 of these fail, then there will be one good one here and another good one here. The separation between those 2 may be too large for the lighting to be at the safe level. So in that case, if that's the case, we say this is a consecutive 2 out of n failed system. If 2 consecutive lights fail, then the system fails. However, if 2 lights fail that are not consecutive, so for example, this first one and third one, we are still okay. Okay, so the consecutiveness of the failures is important here. Unlike a k out of n, regular k out of n system, where any k functioning sufficient, here, you can't have 2 failures that don't cause problems, but when 2 failures are consecutive, then we have a problem. Okay, so here is an example of a 2 out of 4 G system. So this is a 2-line bus, a very simple bus, a bus that consists of 2 lines, going from one side of the chip to the other. Let's say I'm worried about these bus lines, the wires on the circuit board failing, being disconnected. So I provide 4 of these instead of just 2, and then provide switches here so that these 2 lines come from some module that through the bus wants to connect to some other module. So the bus itself is redundant. It has 4 wires. The connections to the module are non-redundant. Now these switches are such that they can connect the 2 lines upward, they can connect them straight through, or they can connect them downward. In other words, the way we control these switches is that they both should be in the same state, connecting upward, connecting straight through, or connecting downward. There are 3-state switches operated in tandem. They both have the same control signal. Okay, now as long as 2 of these wires that are consecutive are okay, then I can sort of send the signals from one side of the circuit board to the other side. So if these 2 are okay, I set the switches upward. If these 2 are okay, I set the switches to send things straight through. And if these 2 are okay, I send them down. But if, let's say, the top one and the bottom one are okay and these 2 have failed, then I'm in trouble because there's no way to set these switches so that I use those 2 good lines, the way I've designed this, of course. Okay, so any 2 of the 4 that are consecutive being good is enough for me to successfully route the signals over this redundant bus. Okay, these systems are not used that often, but because they are mentioned in the literature, I thought you should hear about them. Consecutive K out of N G and consecutive K out of N F systems. G stands for good, F for failed. Okay, so now we come to what we call reliability block diagrams that are the more general version of series and parallel systems. So series and parallel systems are special cases of these reliability block diagrams. So here I've shown a reliability block diagram involving 4 modules, 1, 2, 3, 4. And a success path, as usual, goes from left to right. And this says that if units 1 and 2 are good, I have a success path. If units 3 and 4 are good, I have a success path. Okay, so in order to analyze these, this one happens to be a series parallel system. In other words, I have 2 series subsystems, the series subsystem 1, 2, and the series subsystem 3, 4, and the 2 are connected in parallel. Okay, so the series subsystem 1, 2 has reliability R1, R2, or unreliability 1 minus R1, R2. The series subsystem 3, 4 has reliability R3, R4, or unreliability 1 minus R3, R4. And then the parallel system has an unreliability that is the product of the 2 unreliabilities. Okay, so this is an example. If I have valves like this arrangement of 4 valves happens to be tolerant to 1 closed shut valve and 1 closed open, shut open, shut, close, and shut open. So for example, if this valve is shut closed and this one is shut open, then I can still control, because this one that was shut closed, well, I can use this branch. to direct fluid to the other side. This one is shut open, then I can still use this other valve to control the flow. So it's easy to deduce. Of course, if you have two closed shut, failed shut valves like these two, if these two are both failed to the shut state, then I lose control because these two are shut and liquid will never flow to the others. Also, if these two are stuck open, then this path will be open and I can't control the flow. But one failed shut and one failed open valve will not cause a problem. Whereas remember that in series and parallel system, that wasn't the case. So these are, in a way, more versatile arrangements of modules in order to tolerate failures. Now this diagram here looks similar to that, except that there's this connection. That connection makes this the series connection of two parallel subsystems. So this was the parallel connection of two series subsystems. This is the series connection of two parallel subsystems. And I can easily write the reliability for this. So here's a parallel subsystem. This is its unreliability, units 1 and 3. This is a parallel subsystem. This is its its unreliability. So 1 minus that, it's reliability. This is the unreliability of the second parallel system, 2, 4. 1 minus that is the reliability. And then the product of the two reliabilities, because these two are series. Okay, so series parallel system create no problem. We can use the same formulas that we had. It's a little bit more complicated to write the formulas, but they're straightforward. Okay, sometimes we can draw reliability block diagrams that are not series parallel. So if you look at this particular diagram, it has some elements of parallel and series. So for example, 3 and 4 are connected in series. 6 is connected in parallel with 1 and 2. However, the fact that 5 is connected here causes some problems. I can't use the analysis method for simple series parallel systems to write the reliability equation for this arrangement. So what do I do? Well, one of the methods that I can use is case analysis. I introduced that at the beginning of the lecture. Say, okay, I can analyze this unit system directly. So let me analyze it in the two cases where unit 3 is bad, is unavailable, it has failed. So that corresponds to this situation. Unit 3 is bad, so I can't use it, so it can't contribute to success paths through the diagram. Or unit 3 is good, therefore I can assure that it contributes to success path. So I replace it with a straight connection. If it's bad, I just remove it from it. Now I have two cases that are simpler to analyze because they have fewer units. Unit 3 has been removed. So if I can find reliabilities for these two cases, then reliability for unit 3 times the probability that the system is okay given unit 3 is okay. That's this probability. Plus 1 minus R3, that's the failure probability of R3, times the probability that system is okay given unit 3 is not okay. So once I determine reliabilities of these two smaller systems, I just plug it into that equation and I'm done. Okay, so let's first focus on this one, which is the simpler case. Now look at success path. The only success path in this diagram is 1, 5, 4. And that corresponds to the reliability R1, R5, R4. It's a series system. Notice that I don't take a path such as 6, 2, 5, 4 into account because the paths must go by convention, from left to right. You can't go back the way these diagrams are defined. Oops. Okay, so basically 2 and 6 are immaterial. I might as well remove them too because they never contribute to a success path because the unit 3 is no longer there. So 1, 5, 4, so that's the reliability in the case that R3 is not okay. R3 is not okay. So I plug in this equation into here. What about the other one? The other one, if you look at carefully, is now a series parallel system. It may not look like a series parallel system at first glance, but it is. Why? Imagine you take this connection and put it over here, move it over there. Then you have unit 4 in series with something here. And that thing is the parallel connection of 6 in this branch, and in the upper branch, the series connection of 1 with 2 and 5 in parallel. So in other words, it doesn't matter that there's a line segment here. That's basically, you can replace it with a point. And therefore, you now have a series parallel system. If you did not have a series parallel system, you could continue that case dividing into cases further until you got to a series parallel system. So this is basically, see, product of R4, which is in series with this. What is it in series with? This system, and that's a parallel system. Okay, so its reliability is 1 minus its unreliability, and so on. So please take a look at this equation and make sure that you can convince yourself that it's written correctly. So I plug this one into this part of the equation. And then I have the overall reliability of the system. One way to find, so case analysis is one way. There's a second way to find reliability for a non-series parallel system. So let's enumerate all the success paths. So the success paths in this diagram are 1, 5, 4. That's one path. 1, 2, 3, 4. And 6, 3, 4. There are 3 success paths. Okay, any one of those paths being okay, being available, leads to the system working correctly, the system being available. Okay, so I can consider this like a parallel system shown down here. 1, 5, 4 is one success path. 1, 2, 3, 4 is one success path. 6, 3, 4 is one success path. And write its reliability as a parallel system. Parallel systems, each of its branches being a series system. Okay? However, this gives you an optimistic reliability value. Therefore, the reliability will be less than or equal to what this equation gives you. Why is it optimistic? Because the unit 1, for example, that appears in both of these branches, when you write the reliability equation that way, you assume that those 2 units are independent. In other words, it's possible for this unit to fail, but this unit not fail. Unit 4, similarly, is taken to be 3 different units that can fail independently, whereas there's just one unit 4. And if it fails, then all 3 paths. So this gives you an upper bound for reliability, which in itself is not helpful because We usually want to find lower bounds for reliability, not upper bounds. We want to be pessimistic, not optimistic. However, this equation, if you just multiply it out, as shown down here, so how do you multiply out? You say, okay, 1 times 1 is 1, so that's -1 cancels out with this one. 1 times the -1 times R3, R4, R6 gives you this term. And -1 times R1, R2, R3, R4 gives you this one. -1 times negative this gives you this term. And then you now go here. Positive R1, R4, R5 times 1 gives you this term. Positive R1, R4, R5 times this. So you have R1, you have R3, you have R4 twice in both terms, and then R5, R6. If when you multiply these terms out, you don't raise these individual terms to a power. In other words, R4 times R4 is taken to be R4. Okay? Later, when you have, for example, R1 times R1, you take that to be R1. And it's provable, it's actually a theorem, that if you multiply out that, the terms of that equation that you wrote by simply considering the success path and converting the diagram to this, if you multiply out while not raising terms to powers, in other words, R4 times R4 times R4 is still R4. Okay, so if you get R4 times R4, because these are not independent, therefore you get just R4. Then you get the correct reliability equation. So this is the second way of writing the reliability equation for a diagram such as this one. Just enumerate the success paths, pretend that these are independent paths, write the equation. When you multiply out, just ignore higher powers of each of these R terms, and you get the correct reliability equation. Okay, so reliability diagrams we already discussed. That's one tool that we use in formulating reliabilities. Reliability graphs form a second tool. We don't use these much, but I'm going to present it to you for completeness. So what is a reliability graph? A reliability graph is composed of nodes and links like this, directed edges, connecting a source on the left side to a sink on the other side. So it always has this shape. There's a single source node on the left, a single sink node on the right, and a bunch of arrows connecting these nodes. The arrows are marked by module names. So unlike the reliability diagrams in which the boxes were modules, here the links, the edges, are modules. So this basically says for the success of this particular system, modeled by this reliability graph, module A, module D, module G, and M, if they're okay, then I have a success path. If C, F, H, K, and M are okay, I have a success path. If B, E, J, N are okay, so these are basically success paths as before, except that modules are labels attached to edges, not to nodes. There is one edge here labeled infinity. That means that the edge is sort of like a module that is always available. So for example, A, D, L, N is also a success path. B, D, L, N is also a success path. Okay, you may think, why did I put this edge with infinity on it? Why didn't I just merge these two nodes together? The problem is if I merge, then a path such as CFH, and these two are now the same, CFH, GM also becomes a success path, and I don't want to do that. Okay, so this basically is a way to avoid some paths that I don't want to be success paths to be created. So module failure corresponds to edge disconnect, and an edge labeled infinity is never disconnected. So it's like a module that is always available. All right. The third and perhaps practically most important model of this kind, so we had reliability diagrams, and we had reliability graphs. The fault tree model is something that is used uh, extensively in the industry. It basically provides a way to systematically enumerate failure scenarios in a system. What does that mean? So you start at the top or the tree root with an undesirable event, which we call a top event, and determine all possible ways that the top event can occur. Okay, analysis proceeds by determining how the top event can be caused by individual or combined lower level undesirable events. Here's a simple example. Suppose top event is being late for work. So that's something that you're worried about and you want to analyze and find out, what can possibly cause you to be late for work. Okay? So you come up with these. Clock radio not turning on, or if you use your cell phone not ringing, cell phone alarm not ringing on time. There may be a family emergency that makes you late for work. If you take the bus to work, the bus not running on time can be another cause. So you sit down and basically enumerate all the things that can contribute to that top event. And then some of these can be composite events. For example, clock radio not turning on. If there's a power failure, power outage, and battery is dead. So your clock radio has a battery, can still work when power is disconnected, but it may happen that power is disconnected and the battery is dead so that it doesn't work. So this is an example of a composite event that requires two things, two elementary or atomic events to happen simultaneously for that to happen. So these are some references that you can look at. You probably don't need to study any further than what I tell you in class and also in the textbook about fault trees. But if you are interested, there are many different sources to study about fault trees. So fault tree analysis basically starts by drawing this diagram. So this is sort of a systematic way of thinking about and recording all the things that can contribute to the top event. So you identify the top event. This is the top box here, the root of the tree. And then you say that top event occurs if all three things down here happen. So this is an AND condition, and it's drawn like that. This is an atomic event. So the notation for fault trees, it draws it as a circle. These are composite events, so they're drawn as boxes. Okay, so this composite event occurs if either one of these two atomic events occur. So we draw an OR gate in our fault tree. Okay, so if either of these two basic events or atomic events occur, then this composite event is satisfied. And if this one and this one, all three are satisfied, then the top event is satisfied. On this side, I have an AND of three conditions. Again, one of them is atomic, the other two are composite, and I can continue, for many levels. Other than AND and OR gates in these diagrams, we have K out of N gates when we have a K out of N system. We have XOR gates, although these commonly XOR gates are not used. It's rare that you have a condition that either this happens or this happens, but not both. But just be aware that you can use XOR gates. And you can use this box, which is receives an enabling condition. So if this enabling condition is asserted, this enabling condition exists, then this event causes this event. Otherwise, it doesn't cause. So it's sort of like a switch. It blocks the propagation of these events. And external events is basically something that comes from outside. Okay, by the way, in this slide, there's a first missing here. Identify first level contributors. I don't know how it disappeared from the slide. Identify first level contributors to the top event. Use logic gates to connect first level events to top event, and so on and so forth. Second level contributors, second level gates, and so on. And you can go as much into detail as you want to enumerate all the conditions. So here's an example of a fault tree. In order to analyze and write reliability equations based on fault trees, we need a notion called cut set. A cut set is any set of initiators so that the failure of all of them induces the top event. What does that mean? So for example, if A and B, if those conditions are satisfied, A being satisfied because of this OR gate satisfies that box, B being satisfied because of this OR gate satisfies that, and both of these boxes satisfy the top event because of this AND. So if these two things, A and B, happen, then the top event is satisfied. So AB is a cut set. AD is similarly a cut set. I'll leave it up to you to verify that. And BC is a cut set. Furthermore, these are minimal cut set. A minimal cut set is a cut set so that if you remove an element from it, it's no longer a cut set. So for example, AB is a minimal cut set because neither A by itself is a cut set, nor B by itself is a cut set. So we are interested in finding these minimal cut sets. Okay, just as we can manipulate logic networks, logic gate networks, to find equivalent gate networks, we can manipulate, redraw fault trees into equivalent forms. Okay, something that is perhaps simpler. Now, one of the roots of difficulties in analyzing fault trees is this repetition. So for example, B occurs both here and here. So these two are not independent. If repetition does not occur, then analyzing a fault tree is quite simple. But with repetitions, it's a bit more tricky. Okay, so in order to find the reliability of the system characterized by this fault tree, I can use the cut sets and say, okay, one cut set is AB. AB, in other words, there's no success path if both A and B. So I'm converting it to a reliability block diagram. AD and BC. So if I have all the cut sets, I can convert the fault tree to a reliability block diagram, such as this one, and then analyze this reliability block diagram in the normal way. Okay? Of course, remember I said that B being the same B, these are not independent. So you can't say, okay, B has failed, so this path is not available, but this path is available, and then this path is available. Because if B has failed, then that's not available, okay? So you have to be careful. So here's an example for you to work through. Suppose that the minimal cut sets for a particular tree are AB, AC, AD, and CDEF. Construct a fault tree for this that exhibits that particular cut set. Derive a reliability block diagram for it, and then find the path sets. Now, one application of cut sets is that if the cut set is small, then your system is vulnerable. In particular, if a cut set has just one element in it, that means that element is critical in your system, and its failure can cause system failure. So you want your cut sets to be not too small in order for your system to be robust or reliable. Small cut sets are troublesome. Okay, now the models that we have discussed constitute a hierarchy as shown on this slide. Reliability block diagrams and fault trees with no repetition are completely equivalent. One can be converted to the other. So fault trees with no repetition offer nothing more than reliability block diagram. Reliability graphs are more general than both of these. In other words, both of these can be formulated as reliability graphs, but not the other way around. The arrows go in one way. And fault trees with repeated elements are even more powerful than reliability graphs. Therefore, there is nothing you can do with any of these that you can't do with fault trees if you allow repeated elements. So that's why fault tree analysis tools are so popular in the reliability industry, and there are all sorts of software. I'll talk about the software tools for reliability analysis at the end of the next lecture. Okay, so this is the end of lecture 3. I will record lecture 4 soon and post both of them to the course website. Thanks for listening, and see you in lecture 4.